Measures of spread, section 2.1, pages 47 and 50. Example, Fran has exam scores 71, 81, 91. Sandy has exam scores of 80, 81, 82. Both students have the same mean and median. The mean and median would be 81, but Fran's scores are more spread out. And so we would like to have statistics that measure how spread out a data is in addition to what the center is. And measures of spread include range, interquartile range, or abbreviated IQR, variance, and standard deviation. And we've already computed range and IQR, but so we're going to take a closer look at the variance and the standard deviation. Okay, so we're going back to the same 12 exam scores, 80, 88, 28, 91, 65, 88, 83, and so forth. Here's the formula for computing the sample variance. It's the sigma notation again. The symbol for sample variance is S squared. The sigma notation again, that means sum. Sum is k goes from 1 to n. Xk, quantity xk minus x bar, quantity squared, all over n minus 1. N is the number of scores. X bar would be the mean. Okay, so we can follow the order of operations here. We first want to do what's inside parentheses, each score minus the mean. It's going to be helpful to set up a table. The first column would be each exam score, and the second column, each score minus the mean. And then we want to do the exponents. Exponents will become before addition or division, so we want to do exponents next. So we can put up a column for the exponents, and then we want to do the sum. So it's the sum of that last column, and finally we divide by n minus 1. So that's the procedure we want to do go through for this. So this formula kind of tells us which operations to do and in which order. Okay, so I set up a table here. The first column has the original exam scores, and then it's each score minus the mean, and then square it. And I did the first 10 rows here. Let me just, before we found out that the total was 923, and we actually used that to get the mean. So let's, first of all, that's 923 is the total number for the exam score column, and divide that by 12 scores, and we get a mean of 76.916 and repeating sixes. So I'm going to store that in my memory. Okay, and then so this second column here is each score minus the mean. So I'm going to do 89 minus the mean. So 89 minus, and then I can recall from memory, equals, and that's 12.03 and repeating, 12.083 and repeating threes. So I'm going to write that down. And then while that's displayed, I can push the x squared key. X squared equals, I get 146.0069444. So I'll copy that down. 146.0069444. Okay, and then do the same thing for row 12, 82 minus second recall equals 5.083 and repeating threes. And then while that's showing, I can push the x squared key equals, and it's 25.8402 7778. Okay, so that's rows 11 and 12, and then I want to add up these columns. And with the smaller data sets, you should be able to do this by hand. With a data set this big, I think it's okay to use a calculator on it. But you should know how to do it without the statistics program. You just using the ordinary calculator keys of add, subtract, multiply, divide, exponent. So anyway, we had some rounded numbers here. These threes really go out to infinity. These repeating threes, the repeating sixes also go out to infinity. So they're rounded a little bit. But in theory, if we're using unrounded numbers, this second column, this middle column total should be 0. And we can see we're very close to 0. We're a little bit off because of rounding. And you can use that as a check on your work. If it was very different from 0, then you might want to look to see where you might have made a mistake. Or if you're using unrounded numbers, it should be exactly 0. And if it's not, you could check to see where you might have made a mistake. This column is what we're going to use. This last column total is what we're going to use to compute the variance. So it's the total of all the numbers in this column, 3,746.91 and 6666 and repeating sixes. So that's the number we're going to use on the next step. So the numerator, is the sum. That's the sum of that last column. So that's going to be 3746.91 and repeating sixes. And n is the number of exam scores, which is 12, and minus 1 is 11. So we want to divide this by 11. Let's see what we get here. So it's 3746.91 and repeating sixes divided by 11, and I get 340.6 287.879. Okay, so that's our variance, and I'm going to store that in memory. So push the stow button and equals, and that's going to be in memory now. Okay, and that's our variance. The variance is an important measure of spread because there's a very strong relationship between the variance of a sample and the variance of a population. So it's more work than computing the range or the interquartile range, but it's worth the effort because it's such an important measure of spread. And then related to the variance is the standard deviation. If we take the square root of the variance, we'll get the standard deviation. So I'm going to do I'm going to clear this out and do second square root and then second recall, and it equals, and I get 18.456 something. 18.456131144. Okay, so that's the standard deviation. These exam scores did not have a unit of measure, but if there were a unit of measure, then the unit of measure for the standard deviation would be the same as the unit of measure for the original data set. So if you had the original data was in inches, then the standard deviation will be in inches, and so forth. So there's a lot of important theorems about the standard deviation, so that's also important. It's it's actually sort of related to the variance in the sense that if the the variance is big, the standard deviation will be big, and if the variance is small, the standard deviation will be small. One of the theorems is useful theorems for any data set. At least 75% of the data is within 2 standard deviations of the mean. So, so for these exam scores, 75% of the score should be, if you go 2 standard deviation below the mean, it's 17 minus 18 minus 18 is 41. Two standard deviations above the mean, 77 plus 18 plus 18 is 113. And so at least 75% of the score should be between 41 and 113. In fact, in this case, 11 out of the 12 scores, or 92% of the scores, are between 41 and 113. So anyway, that's one of the theorems that's useful for the standard deviation. I mentioned that the middle column total should be 0. Here's a proof. We're not going to be doing a lot with proofs, but this is one that I would like you to know. Prove that for all data sets, the second column total is 0. In other words, prove that the summation as I goes from 1 to n, each exam score xi minus the mean is equal to 0. And here's the proof. By definition of sum, we can write this out as the first score minus the mean, plus the second score minus the mean, plus etc., plus the last score minus the mean. That's by definition of sum. And then because the order doesn't matter for addition, commutative and associative properties of addition, we can put the x1, x2, x3, etc. together and put the x bars together. So just rearranging the order. Subtraction is not exactly commutative, but if you take the sign with you and treat it like an addition, then you can change the order for subtraction also. So this, we're subtracting x bar n times here, because that's the number of exam scores. So that we can write that as n times x bar, because we're using multiplication to represent repeated addition. And then these first terms, we can write that, go back to sigma notation again. x1 plus x2 plus etc. plus xn can be written with sigma notation. That's the summation as I goes from 1 to n of xi. And then we can use the definition of x bar. So x bar is the mean. That's the sum of all the exam scores divided by n. And we can cross cancel the n's. And we have the sum minus itself, which is 0. Anything minus itself is 0. So that concludes the proof, and that concludes this presentation.